Hello everybody, my name is Kyle. Today we're going to be going over as many of the physics problems as possible, so go ahead and follow along. Um, I will have the questions in the description below, and also I'll kind of have it on the side here. But okay, so let's start with the first problem. Okay, so a girl attaches a rock to a string, which she then swings counterclockwise in a horizontal circle. The string breaks at point P in the figure, which shows a bird's eye view. Which path A through E will the rock follow? So, um, just from off the bat, you can convince yourself that the answer to this problem is B. And the way you can do this is one of two ways. You could just try it out for yourself. You could take a video of yourself swing something around like a yo-yo, and let it go and see where it goes. The other way you can think about this is inertia. Um, when you release it, the velocity vector is pointing in this direction. It's basically straight. And so once you release it, if you don't take into account like gravity or anything else like that, it should go in a straight line. So B. Okay. There's a lot of noise in the background, but just don't mind that. Number 2. A truck is using a hook to tow a car whose mass is 1/4 that of the truck. Okay, and just as something to mention, um, I haven't looked at the answer to these questions, so hopefully I'll get all of them right. But okay, number 2, a truck is using a hook to tow a car whose mass is 1/4 that of the truck. If the force exerted by the truck on the car is 6,000 newtons, then what is the force exerted by the car on the truck? So let's go ahead and look at this. So I think we can use a law here, which says that the force, once you exert a force, an opposite and but equal force is also exerted, which is not a very technical description, but um, yeah, if you have yeah, if the force exerted by the truck on the car is 6,000 newtons, the force exerted by the car on the truck should also be 6,000 newtons. So there's equal and opposite forces at play. So let's look at the answer for number 2 and see if that's correct. So number 3, when a 45 kilogram person steps on a scale in an elevator, the scale raised a steady 408 newtons. What is the acceleration of the elevator? Okay, so so if we draw a picture of the elevator here, and you have the scale here, and then you have the person. Okay. So what we want to do is we want to draw a force body diagram of the of the of the forces on the scale. So some of the forces I can draw, I promise. Some of the forces is equal to the mass of the person times the acceleration. So we don't really have much to go by, but what we could do is we could also think about it like this. The acceleration is usually 9.8 usually, but if you're in an elevator, it can either increase or decrease. So um, if the elevator was moving, okay, so if the elevator was not moving, he would weigh 45 times 9.8. That's 441. So if we're looking at this now, it's the scale reads a steady 480 newtons, right? So if you're still, it's 441. Again, we're trying to go through this as quickly as possible. So obviously we're not standing still because it's different from, our final answer is different from what we calculated. It's actually 480 newtons. So it's asking us what is the acceleration of the elevator. You can set up the equation like this. You have the mass of the person times the acceleration of gravity, 9.8, plus the acceleration of the elevator, and then that would give you your answer. So you have mass. Here that is 45. Okay, so putting that all in the calculator, 480 divided by 45 is equal to that minus 9.8 gives you 0.87. If you solve for A, you'll find that acceleration is equal to 0.87. All right, and is that the correct answer? Number 3. Yes. Yes, it is. Okay, so let's go ahead and see number 4. If I weigh 741 newtons on Earth at a place where g equals 9.8 and 5,320 newtons on the surface of another planet, what is the acceleration due to the gravity on the planet? So, here's the Earth. Here is the new planet. Acceleration here is 9.8. 9.8. Acceleration here is question mark. So first, we should find the mass of the person at Earth, and then we could, because mass stays the same, assuming that you don't really do anything, but assuming that the mass is the same, we can figure out the acceleration. So over here, 741. Sorry, I'm supposed to be using blue here. 741 is equal to mass times 9.8. Okay, 741 divided by 9.8. That is 75 kilograms. So we can apply that to here, where you or someone, or you, 5,320 newtons is equal to mass, which we know as 75 because mass doesn't change, we're assuming that, times acceleration, which is what we're trying to find. And if we do the math, we'll find that the acceleration is very equal to 5320 divided by 75. That is 71. If you take into account significant figures, it's actually 70.9. So, okay, number 5, sorry. Inside of a train, a ball of weight W is hanging by a light wire at rest from the ceiling. The wire makes an angle theta with the ceiling as shown in the figure. What is the tension T in the wire? So for this one, what we should do is write the force body diagram. So we have the ball here. That's a really great drawing. Let me go ahead and draw it better. We have theta. So if we just look at it, let's determine the point at which we'll draw a force body diagram over here. Right there, we have a couple of forces. We have the tension here, it's denoted as T, and then we have the weight of the ball. So, and we have the angle theta here. If we draw a 90-degree angle, okay, so what we could do is we could split this up into x and y vectors. So we have the sum of the forces in the y direction is equal to 0. So it's pretty easy. This is a 90-degree angle right here. So the angle inside of this triangle, the angle inside of this triangle with this red theta is equal to 90 minus theta. 90 minus blue theta. Okay, so what is the tension T in the wire? T, if you remember from your trig, blue T is equal to what is this? Sine, cosine. Yeah, cosine. Okay. Slow down. Remember that cosine of theta of adjacent over hypotenuse. Adjacent is t. Sorry, adjacent is not t. It's the t y, and then you have tension. Hypotenuse is tension. So the y component of tension is the adjacent over here. It's the y component. And the hypotenuse is obviously the entire thing. So that's tension. So in order to solve this, we need to find what Ty is. Now, we know that the sum of the forces in the y direction is equal to 0 because it's basically, there's no acceleration in the y direction. So there's no acceleration in the y direction. We only have two forces currently in our force body diagram, and that is Ty minus W. And basically what that means is we can sub in W over here, and we can say that the tension T in the wire is equal to W, green W, over cosine of theta, cos theta. That's quick. But okay, let's see if I'm right. 5. Yeah, that was really easy. Okay, let's go ahead and do number 6. Future Kyle here. I'm taking a look back at number 6, and I think I made a little bit of an error, but I think y'all can also learn from this one too. So first I thought that I could use f is equal to kx. And the problem with that is, okay, well, let's go ahead and read the problem. If 4 joules of work are performed in stretching an ideal spring with a spring constant force of 2,500 newtons per meter from equilibrium, by what distance is the spring stretched? So at first I thought, oh, it's 4 joules. I could just put that into here. But the units don't actually work out. So the force, the units of force are basically newtons, and the units of work are joules. So they gave us a unit of work, and it also says 4 joules of work. But if you're going really quickly, this is one of the things that you can kind of mess up with. So once we know that, we're not going to use this equation, but instead we're going to use this equation. 1/2 kx squared. So yeah, so just be careful about units, and also reading the problem slowly. Yeah, basically we know k, so that's 2,500. And we also know work, which is 4 joules. Therefore, we can solve for x. And yeah, yeah, that's just algebra now. But yeah, just be careful about this. Okay, number 7. In a carnival ride, passengers stand with their backs against the wall of a cylinder. The cylinder is set into rotation and the floor is lowered away from the passengers, but they remain stuck against the wall of the cylinder. For a cylinder with a 2-meter radius, what is the minimum speed that the passengers can have so they do not fall if the coefficient of static friction between the passengers and the wall is 0.25? Okay, if you're looking at it from the top, we have basically this big circle, and there are people here. These are the people's heads because we're looking at it from the top. And basically what this is basically what's happening is this ride is going around like this. It's going around so quickly that the people are pushed. They're being pushed into the wall. So like that. Um, it's kind of like the teacup ride in Disneyland, but not really. So what is the we're trying to find the minimum speed so the passengers do not fall. Okay, so now if we look at it from not from the top but from the side, and we just simplify it so that we're looking at one person. This is the wall. The coefficient of friction between the person and the wall here is 0.25. I'm just writing down all my nodes. Now we're gonna we also know that the R is 2 meters. 2m. Okay, so let's go ahead and draw a force body diagram right here. So here we go. So we have the force of the person being pushed into the wall here like this. And then we also have the force of the wall pushing on the person. There is no acceleration in the x direction, because if there was, the person would either go through the wall or the person, there isn't enough. So let's go ahead and solve the problem. What is that? Okay, some of the forces in the x direction. A lot of distractions here. Oh well. Some of the forces in the x direction is equal to 0. So that is equal to forces here. The force of the person being pushed against the wall. Force of centripetal acceleration minus the force on the wall. Or normal force. Normal force. Yeah, I actually drew it right. Okay, so the other thing to notice is that the sum of the forces in the y direction are also equal to 0. Forces in the y direction equal to 0. So what are the forces in the y direction? So in the y direction, we have the force of gravity going down. And then we also have the force of friction. So here we go. This is friction, and this is gravity here. Now, we know that the force due to gravity is equal to mass times gravity, and the force due to the frictional force here, that is equal to mu, which is 0.25, times the normal force, Fn. Now, if we look above here, we can solve the equation and find out that this is also equal to Fn is equal to Fc. Now, what is Fc equal to? The centripetal force. So what is the centripetal force? It is mass. Centripetal force is equal to mass times acceleration. Mass acceleration in this case is v squared over r. All right, so now that we have all of these things, we can combine them. And then we can say that mg is equal to mu m v squared over r. Now the nice thing about this equation is the m's cancel, and v is equal to g times radius over mu square root. So hopefully that makes sense. Number 8, a 40 kilogram box is being pushed along a horizontal smooth surface. The pushing force is 15 newtons, directed at an angle of 15 degrees below the horizontal. Okay, what is the magnitude of acceleration of the crate? Basically, you have the surface, you have the crate, you have the person pulling it like this. I don't know why he's pulling it like this, but he is. And the thing is, running out of colors, we have an angle here that is theta. So it's 15 degrees below the horizontal. So theta is 15. 15 degrees. What is the magnitude of acceleration of the crate? So some of the forces is equal to ma. So we have a horizontal smooth surface, which means that there is no friction. The pushing force is 15 newtons. Sum of the forces is equal to ma, which is also equal to 15 newtons. 15 newtons. Now, if only we knew the mass, we could find the acceleration. Oh, we know the mass. It's 40 kilograms. This we can solve for that because we know that m is equal to 40 kilograms. Okay, and basically acceleration is equal to 15 divided by 40. Yes, which is 0.375. All right, okay, on to the next problem, number 9. The figure shows a block of mass m hanging at rest. The light wire fastened to the wall is horizontal and has a tension of 38 newtons. The wire fastened to the ceiling is also very light, has a tension of 59 newtons, and makes an angle theta with a ceiling find the angle theta. Okay, so this is just drawing force body diagrams and seeing if we don't get stuck. All right, so let me go ahead and show the second part here. Okay, when it says the wire fastened to the ceiling is also very light, that means that the wires don't have any mass. They have fastened to the ceiling is also very light. It has a tension of 59 newtons. This has 59. Do we know m? We don't know m. Okay, that's fine. So let's go ahead and draw our force body diagram here. So if we go there, we have a couple of forces. We have in the x direction here, we have 38 newtons, 38. We have 59. And then we also have m. So it seems that we have, I believe, I'm writing the equations in my head right now, and I believe we have two equations, two unknowns. And so we could just solve for those things. Okay, so the things that we have to know are that the sum of the forces in the x direction is equal to 0. Sum of the forces in the x direction is equal to 0. And the sum of the forces in the y direction are also 0. Again, I'm trying to do this as fast as possible, so please excuse the and also my tablet doesn't really work. For this one, I would say let's just look at the force body diagram. So let's make going over here positive and the other way negative. So we can say 38 minus. So the thing to realize is that there is an x direction. You can break the tension for the for this other one, the 59 Newton one, into two parts. So there's the x direction and the y direction. So let's just take the x direction of that. We have theta here. Theta is over here, right? So we have hypotenuse that's over here. That's 59. So that's cosine. So 38 minus the cosine of theta times 59. Is that correct? So cosine of theta is equal to adjacent over hypotenuse. Yes, this is correct. 38 minus the cosine of theta is equal to 59. We could just solve this equation for theta, right? So cosine, you say cosine of theta is equal to 59 over 38. So yeah, this is sometimes what happens. You have an idea of like what you're supposed to do, and then you realize that the problem is actually simpler than what you thought it would be. So we're gonna just take the inverse cosine here. Cosine minus 1 times 59 over 38. 59 over 38. Yeah, we have two equations and two unknowns, but the properties of these equations don't make it so that we can just solve for theta using these two equations. And also it's easier for us to just solve for theta. There it is. Okay, so there we have it. Great. Okay, number 10. A 3 kilogram and 5 kilogram box rest side by side on a perfectly smooth level floor. A horizontal force of 32 newtons is applied to the 3 kilogram box, pushing it against the 5 kilogram box. As a result, both boxes slide along the floor. How hard do the two boxes push against each other? So for this one, I kind of had to look up another explanation online to kind of understand. And so if I was going to put down my reference, it would be the organic chemistry tutor. So I'm kind of copying basically how he explained this. So go check him out. He's really good. But so let's go ahead and draw it out. So first of all, we have a perfectly smooth level floor, which means that there's no friction. And if we draw two boxes here, we have the 3 kilogram box and the 5 kilogram box. Okay, that's a nice looking box. So we can calculate the acceleration of the entire unit as a whole first. So we can look at it as a very big box that is 8 kilograms in mass, and we can calculate the acceleration this way. So we could say that the sum of the forces in the x direction is equal to m1 plus m2. That's 8, right? Times acceleration is equal to the force that you put in the beginning. So this force is 32 newtons. So it's almost like so you're pushing both of the boxes with 32 newtons. So usually this is how you would find the acceleration of the entire system. If you had a system of say 3 boxes, you would do the same thing. Now, in order to solve for the box in the middle, so this is the 3 kilogram one, this is the 5 kilogram one, what you would have to do is look at it and isolate it. So if you just isolate the box, so this is 3, you can draw your force body diagram on that box and also draw your equation. So we have two forces. We have 32 newtons, but then we also have another force pushing against the box. So this is what the question is looking for. It's looking for the forces that the boxes push against each other. Another way to say this, as the organic chemistry tutor also described it as the contact force. So let's go ahead and write this. So the sum of the forces in the x direction is equal to is equal to 32 minus the contact force. So let's just say Fc is equal to, say equal to here, m1, which is 3, right? This is 3, times acceleration. Now we know what acceleration is. Acceleration, if we solve for acceleration here, that is 32 divided by 8. Because m1 plus m2 is equal to 8. So we just plug that in here. We know that this is 3. We know this is 32. We can solve for the contact force. So that's how you basically solve for the contact force. Now let's go ahead and extend this problem. So say we have 3 3 boxes because this is what you may see in your exam, right? So say we have 3 boxes, so 3, 5, and 2. And instead of trying to find, so let's try to find the contact force here and here, okay? So in order to set up this problem, it's basically the same thing. Let's pretend also that this is being pushed along 32 newtons. Bam, bam. Okay, so now the new question that I've proposed, because I don't only want to like copy from organic chemistry tutor, is okay, let's go ahead and find the contact force between box 3 and 5 and between box 5 and 2. So basically, we do the same thing as before with a little bit of a tweak. So first we solve for the overall acceleration by treating all the boxes as one unit. So acceleration here, whoa, that doesn't look like an A. Acceleration in this regard is equal to 32 divided by 3 plus 5 plus 2. 3 plus 5 plus 2, that is 10. So that's basically the acceleration. Now, if we want to find the contact force between 3, 5, and 2, we basically isolate the first box, so that's 3. And then we say the sum of the forces in the x direction is equal to m1, which is 3, times a, right? Is equal to, so if you draw a force body diagram here, we have 32 newtons being pushed here against the box, and then we have the contact force, F of C. So it's basically the same thing as before. So 32 minus FC. So how about the second part though? So this is where it gets kind of cool. So if we can actually kind of box 3 and 5 as one unit. So we have 3 boxes, right? So if you wanted to find the contact force here between box 2 and 3, we can group the 3 kilogram box and the 5 kilogram box together as one unit. So that's blue. And we can take number 2 as the final box. So this would become an 8 kilogram box and 2 kilogram box. Now that we have further simplified the problem, we can solve this problem the same way as we solved the first problem. Only instead of a 3 kilogram box and a 5 kilogram box, we now have an 8 kilogram box and a 2 kilogram box. So some of the forces, wow, that's great writing we have going on over here. Sum, there we go, the forces in the x direction is equal to m1, where m1 over here is 8, times the acceleration. Again, acceleration stays the same. Acceleration, as we saw before, is 32 divided by 10, in this case, is equal to 32 minus the contact force. And yes, I think I'll leave the link to the Organic Chemistry Tutors video in the description below as well. Okay. Number 11, 3 boxes are connected through light strings and rest on a smooth horizontal floor, as shown in the figure below. Their masses are 2 kilograms for box 1, 3 kilograms for box 2, 50 kilograms for box 3. A force T3 equals 50 newtons is applied on a string attached to box 3, which then pulls on the other 2 boxes through the strings. What is the tension in the string that connects box 3 and box 2? We have our smooth floor here. I'm going to make it blue this time. Let me go ahead and make a new page. So if we have a smooth floor, box 1, box 2, box 3, we have here we have 50 newtons. And over here, this is what we're kind of trying to find. So we can simplify this problem a little bit. So 2 kilogram, 3 kilogram, and 5 kilogram. So this is 2 kilogram, 3 kilogram, and 5 kilogram. We can simplify this problem as this. So we have a 5 kilogram box here. That's connected to another 5 kilogram box. So basically what I've done is I've combined these into one box. And we're still pulling on this box here as with 50 newtons. So we can set up our force body diagram over here. And what we have is we have a force to the right, and then we also have a tension to the left. So let's call this T. Now, this 50 is greater, this 50 newtons here is greater than T, obviously, because if it was less than T, then we would be going to the left. So let's go ahead and write this down. So some of the forces in the x direction is equal to 50 minus T. That is equal to M1, which is 5. In this case, it's 5 kilograms. It's this one, times acceleration. Now, to find acceleration, we can kind of use the trick that we did from before, where we can look at all of the boxes and say that they're one box and calculate the acceleration. So we can take this and we can further simplify it to this. So this is, we basically have a 10 kilogram box. Okay, let me stay consistent, write it in green here. And we are pushing on it as 50 newtons. So the thing about this is we can say 50 is equal to, if we use the sum of the forces, is equal to M1 plus M2 plus M3, which is 10, right? This is 10. 10 times acceleration. And then acceleration is equal to 50 divided by 10, which is equal to 5 meters per second squared. So now that we've found the acceleration, we can plug in acceleration over here. We know what M1 is, and that's 5. And then we could basically calculate T. So the tension is equal to 50 minus 5 times 5. So let's go ahead and move on to number 12. So a flatbed truck is carrying a 20 kilogram crate up a sloping road. The coefficient of static friction between the crate and the bed is 0.4, and the coefficient of kinetic friction is 0.3. What is the maximum angle of slope that the truck can climb at constant speed if the crate is to stay in place? Okay, so new page. Okay, so we have basically a slope. We have a load that is being dragged upwards here. And we're supposed to find theta. Do we know the mass? Mass 20 kilograms. Yes. So this is 20 kg. And the coefficient of static friction is 0.4 here. 0.4. I'm going to draw an arrow for the friction between And then also, the other clue that we have over here is that the truck can climb at a constant speed, which means that some of the forces in this direction is equal to 0. So here is the slope of the road, and here is the crate. So the crate is being pushed this way. It's being pushed straight. It's not going up or down the slope. It's being pushed straight. So because of friction, there is a maximum angle that you can go. And if you go any higher, it's going to start slipping down, right? And so the question is, how far can I go in terms of the angle where this doesn't start slipping? So let's go ahead and try to solve that. I'm gonna kind of do the same thing as I did before, where I'm going to rotate the axes and make this positive x, and this positive y. And what I'm going to do is I am going to say that positive x, or the sum of the forces in the x, are equal to 0. So it's not slipping. This crate is not slipping. And the reason for that is because there is a friction. So we know the weight of the crate, right? So the crate is going down, but then there's also this frictional force. And those two forces are equal, right? So let's call this F. Now, we can continue here saying that Fs, sorry, this is red, Fs minus Fx, or the force of the crate going down, that is equal to 0. So now we have to find F somehow. So now, do we know the weight of this block? Yes, we do. And what we can do is we can find all of the components. So if we just look at the angles carefully, we know that theta is over here, which means that theta is also over here. This is getting kind of complicated, but basically this is 90 degrees minus theta. 90 minus theta. And if we're trying to find this part, we're trying to find the force vector that's adjacent to it. So basically what I'm saying is F, basically what I'm saying is the cosine, let's go ahead and use red, cosine of 90 minus theta is equal to adjacent over hypotenuse, so that's adjacent F over the hypotenuse, which is weight, over W. Right, this is W. We know that F of S, we're almost there, I believe, is equal to mu times the normal force. And the normal force here is the opposite of this. It's the sine. So it's the other green vector. So this is the green vector that we solved for. That's F. And this is F. So the normal force is basically, let me go ahead and draw it over here. We have blue box we have the normal force, Fn, Fn, and then we also have the this basically, this is the horizontal component, and this is weight again. So this is theta. This is theta. And basically, if we're going to try to find f of n, I've kind of simplified things over here, but this is, I've kind of simplified things here, but this is the normal force. So the normal force over here is equal to the y component of the blue vector. So if you look at the sum of the forces in the y direction, that is equal to f of n minus the y component of the weight. So let's say weight, y component of weight is equal to cosine of theta times the weight, the actual weight. So the actual weight is equal to mg. The other way of writing this, hopefully this isn't confusing, is cosine of theta. Kind of skipping some steps here. So, but cosine of theta is equal to adjacent over hypotenuse, where your adjacent is, if you look over here, the y component, wy, and your hypotenuse is your actual weight, which is mg. mg. Okay, so cosine of theta is equal to wy over mg. That will give you this equation where wy is equal to cosine theta mg, which you can then substitute over here. F of n is equal to, all we were trying to do was trying to find the normal force. That is equal to cosine theta mg. We can substitute that here, where this is equal to mu cosine of theta mg. What we can say is this cosine of 90 minus theta, using a little bit of trig, we can say that's sine of theta, right, is equal to f, which is cosine, f, which is, yeah, mu cosine theta mg. All over weight, which is mg. So the mg's cancel out. Great. And then what we're left with is sine over cosine. That's equal to tangent. So basically what we have is sine of theta over cosine of theta is equal to mu. Oh my god. This is equal to mu. And sine over cosine, if you remember, is equal to tangent of theta. So we can write this as tangent of theta is equal to mu. And if we take the inverse tangent of both sides, we'll find out that theta is equal to the inverse tangent of mu. Yippee. Great. Let's go ahead and do three more, and then I think I'll call it a day. The figure shows a block of mass m. I'm back. Okay, so number 13. This figure shows a block of mass m on a 20-degree slope. The block has coefficients us, mu k. Okay, Nala pulls the block parallel. Blah, blah, blah. What is applied for just before the block starts moving upward? Okay. Finally, some peace and quiet. So we have m. They don't give us a mass, so that implies that we can solve this without knowing the mass. So we have the weight of the block, of course, which can be split up into two parts, right? This way and this part. And then we also have theta over here. And as you know, if theta's there, theta will also be here. The other thing that we have is that we have friction. So this is static S. And then we also have the force that we're actually solving for. Now for this, of course, because it's inclined, we're going to rotate the axes by 20 degrees. So this is positive x. So the sum of the forces in the x direction just before she starts moving the box is 0. There's no acceleration, there's no velocity. Well, what's more important is the acceleration, obviously. So sum of the forces is equal to 0, which means that there is the force going up. That's what we're trying to solve for. Minus f of s minus the weight in the x direction, right? So we have these forces. All right, so basically F is equal to f of s plus wx. Static friction plus wx, weight in the x direction. So if we know what f of s is and we know what w of x is, then we can solve this. So f of s is equal to mu s times normal force f of n. Now if we look at this again, and we look at this mass here, again, f of n is pointing upwards. And we have f of n is equal to wy, right? Because when it's like this, if it's not falling through the slope, then the sum of the forces in the y direction is equal to 0. So let's go ahead and draw that. Sum of the forces in the y direction is equal to 0, which is equal to f of n minus wy. So f of n is equal to wy. What is wy? Wy, so this is our angle here. This is our weight. So we use cosine. We know that cosine of theta is adjacent over hypotenuse, where adjacent is wy, what we're looking for, over w, right, which is weight, which is mg. We don't know what weight is, it's just we just know that it's m times g. So anyways, wy is equal to cosine theta times mg. All right, so mu s cosine theta cos mg theta times mass times gravity. Okay. Now, what is wx? Wx is this part, right? So you don't use cosine anymore, you use sine. So wy is equal to cosine theta times mg. So therefore wx should be equal to sine of theta mg. In order to find the force, F is equal to mu cosine theta sec here. Mu as cosine theta mg plus sine theta mg. And that's how to solve for number 13. So let's go ahead and look at number 14. A 16 kilogram box is pushed down an inclined plane that makes an angle of 19 degrees with a horizontal. The applied force is parallel to the inclined plane and its magnitude is 50 newtons. If the coefficient of kinetic friction is 0.4, at what rate does the box accelerate along the slope? Kind of the same thing, you just have it actually accelerating down the slope. So friction is going this way. You are pushing the box, so it's going down that way. And obviously the weight is going down this way. So those are the forces. And we are going to rotate our axes. We're going to make this positive x, just to make things easier. And this positive, we'll think about positive x and positive y later on. But we're going to make downwards as positive x in that direction. So some of the forces is not equal to 0. Some of the forces in the x direction is equal to ma, right? And it is equal to the weight in the x direction. The weight in the x direction, because as you can see, the weight has two components. So we have a component going down this way, so that's the weight in the x direction, plus the force minus the frictional force. We know that this angle is theta here. This is theta. And that we know this angle is theta over here. Weight in the x direction is equal to mg. The question is whether or not we use cosine theta or sine theta. So this is theta, it's sine theta, obviously, because it's opposite. So sine theta plus 50 minus mu s. We have mu s, right? Yes, kinetic friction is 0.4. So this is 0.4 times the normal force. The normal force is this force. The normal force is equal to this force. So that is equal to mg cosine theta. I hope you are seeing a pattern with these problems. So if one is cosine theta, the other is sine theta. But hopefully in the exam, they might try to trip you up here. So always draw it out to figure out whether it's sine theta or cosine theta. To find the acceleration, you just divide everything by the mass. So divide everything by the mass. So divide by the mass, and then you take all this and divide by the mass, and that should give you your acceleration. So 15. A 200-gram hockey puck is launched at an initial speed of 60 meters per second up a metal ramp that is inclined at a 30-degree angle. The coefficients of static and kinetic friction between the hockey puck and the metal ramp are mu s, mu k, 0.4.3. What vertical height does the puck reach above its starting point? Hello everybody, Future Kyle here. So I actually did the problem for the first time, and I did it wrongly for two reasons. Number one, I was looking for the distance instead of the height. So that's what I get for reading the problem too quickly. And number two, I don't think I set up my equations correctly. And this is something that I hopefully you guys will learn from me. So I thought of the problem like this. So I thought that the kinetic energy would then give rise to the potential energy plus the frictional force, or as your professor would have it, WNC, or non-conservative force. So this F here is the frictional force, or non-conservative work. That is correct. What is not correct is all the rest of the math that I did over here. So I'm going to redo it. The main thing that I didn't do correctly was I didn't correctly come up with the right equation for the frictional force. So potential is equal to mgh, and we're actually solving for h. So that's all well and good. Kinetic is equal to 1/2 mv squared. It's pretty easy. We have m, we have v. We're looking for h. We know what g is. So now, how do we come up with the equation for the frictional force? We have our frictional force. We can basically say that's basically the same thing as the non-conservative force that your teacher talks about. What I did wrong before was I thought that it was equal to F of k, which is the kinetic frictional force, times the cosine of theta times distance. And this is almost correct, but it's definitely not correct. So the right equation to use, is mu k times mg times the cosine of theta times the distance. So this is almost the same thing as, this is almost the same thing as f of s, right? This is almost the same thing as f of s. But this is not equal to f of s, which is what I wrote down earlier, times the cosine of theta times d. So if you're getting like cosine theta squared or something like that when you're doing these problems, usually you're probably on the wrong track. So just something to watch out for. Now that we're using the correct equation, We know what m is. We know what g is. We know that what mu k is. We know what cosine theta is. Do we know what d is? No. Um, but what we can do is we can change this equation so that it has h instead. So what we're actually looking for is h, not d. So let's go ahead and do that. If you don't know what I'm talking about, just go ahead and follow this, and it will make sense in the end. So we can relate the distance that the puck moves up the slope and the height that it also changes with sine. So we can say sine of theta is equal to opposite over hypotenuse. So now this is unfortunate that our variables do this, but opposite in this case is h, not the hypotenuse, over d. Right? Now we can say that distance is equal to the height, not the hypotenuse, over the sine of theta. All right. So if we sub that back into here, we can say that this is equal to mu k mg cosine of theta. So you have d times the cosine of theta over the sine of theta. Cosine of theta over the sine of theta, that's equal to 1 over the tangent of theta. So let's go ahead and write that down. 1 over the tangent of theta. Okay. So yeah, this is just basically substitution. So we're basically substituting h over sine of theta for distance. And we find this. Now that we've done that, we can finally have f here. So this is, again, to reiterate, this is kinetic energy. This is potential energy. We have a plus sign. And then we have the frictional force, which is the non-conservative work, which we just found out is mu k mg d times 1 over tangent of theta. 1 over tangent theta. All right. Now that we've done all that, we can actually solve for h. So this is the height. Sorry. This is height. You can actually solve for height here. I said this was the distance, and this was actually the height. To solve for height by isolating it. And height is now equal to kinetic energy, 1/2 mv squared, 1/2 mv squared, all over mg plus mu k mg 1 over the tangent of theta. And of course, the masses cancel out. So the masses cancel out over here, here, and here. And you're basically left with 1/2 v squared over g plus mu k g times 1 over the tangent of theta. Now, that was quite a lot. I think I'm done for today. If you have any questions about this or anything else, you can contact me because I'm only sending this out to a few people. Feel free to reach out, and yeah, I'll see you all next time.